Hello everyone, in this video we are going to look at two specific carbonyl compounds that we can use for the synthesis that can lead to a more exclusive result from the reaction. The first carbonyl compound we are going to look at is have a name called acetoacetic ester. So acetyl group is a group that looking at something look like this. This is your acetyl group, and acetic ester is to have a ester, and specifically we usually use a ethyl acetate. So this compound here is called ethyl acetoacetate. So this is our starting material. So the beauty of this starting material is that it have a alpha position that's sandwiched between these two carbon-oxygen double bond. So the hydrogen on this alpha position is dramatically more acidic compared to the hydrogens that at this alpha position. And in general, the pKa of this alpha position hydrogens is about 19. However, for this red one sandwiched between these two carbon-oxygen double bond, this pKa value for these hydrogens is around 10.7. Okay, so that is this compound. So this compound in general is basically is a beta ketone ester. We have ester right here, so this is your alpha position, and the beta position you have a ketone. So this is beta ketone ester. That is the structure feature and acidity feature of these alpha protons. So why this matters? So if we are going to introduce a base that, for example, we introduce a sodium isoxide, and relatively this base is relatively strong base, and the conjugate acid, the pKa, is about 16. So for this base, the blue hydrogens on the end is not acidic enough to be deprotoned by this base. However, what is in between here, this red hydrogen is acidic enough to be deprotonated to form a very, very stable enolate. We are going to do that process, and it will deprotonate this. So what we are going to have here is this very resonance stabilized enolate and can act as a nucleophile. We are going to also draw out the resonance, and we are going to have 3 resonances to show that this negative charge is very stabilized. Okay, and another one, this can also go this way. That gives you another resonance enolate. Okay, so in this way, what we have here is we have a very strong nucleophile at this middle alpha carbon. And then if we have a acylbromide, for example, we throw in a isobromide, then what will happen here is this will attack this carbon to undergo a substitution reaction that will give us the substitution alkylation at this alpha position. So after that we are going to introduce the acidic condition that it basically is a hydrolysis of the ester. So when we have the ester undergo the hydrolysis, that ester will become as carboxylic acid. So on this side, now we are going to have a carboxylic acid. So you may ask, why we do this? the whole key point of beauty of this reaction is that we are going to introduce exclusively of this alkyl group on one side of this carbonyl group. We are not going to do anything on this side, only going to introduce the alkyl group on this side of this potentially ketone. So by keep going, the next step is that we are going to heat up this reaction mixture. The reason why is we are going to put in some energy into here, and what's going to happen is we are going to rotate this bond that's going to let this molecule undergo a so-called decarboxylation. Let me draw this out first. So what we are having here is that bond will rotate, that this time hydrogen will be, hydrogen OH group will be on this side. So this is my, now after that, this process going to kick out a carbon dioxide molecule. So this is going to grab this hydrogen, and the bond between oxygen and hydrogen now will go down to form carbon-oxygen double bond. And then at the same time, this bond will need to break to form this double bond between the two carbons. So the outcome of this process is, let's draw this out first. We have the oxygen-hydrogen bond form. We have this double bond between these two carbons, alpha and beta carbons, and then alpha and carbonyl carbons, and then we have this double bond. And at the same time, what we are going to have is this portion right here. So you have a carbon-oxygen double bond, another carbon-oxygen double bond that give us a carbon dioxide. So carbon dioxide is a gas, so this thing will bubble out of your reaction and remove the product. So that is a driving force. What we see here, this process is called decarboxylation. So we kick out a carbon-oxygen double bond and also remove that carboxylic acid group. So that is our product for this. And what we are achieving here is a enol at this moment. So enol will undergo a enol ketone tautomerization. So this will be our final product right here. So what we are seeing is from an acetoacetic ester, what we can get is a alpha position substituted. This is alpha position. We are getting a alpha position substituted acetone. So this part is your acetone that's come from the beginning, and we exclusively substitute on one side of this alpha carbon. This side alpha carbon that is originally come from the alpha position that's sandwiched between the carbon-oxygen double bond. So that is acetoacetic ester. So what we achieve here is alpha position alkylated acetone. So you have this side, and then the other side you have this R group introduced. So this one, we introduce one R group. You can also keep going to introduce two R group at this alpha position to give you the dialkylated acetone. Now let's look at one example. If we start with our beta ketone ester, and the first step, we are going to put in the strong base and give a primary alkyl halide. What we are going to achieve here is this sandwich between position have the ethyl groups. Now before we introduce the acid to hydrolyze the ester, what we are going to do is we are going to keep going to add another alkyl group. So the next step, we will repeat to introduce the strong base, form this enolate, and introduce another primary alkyl halide. So in this way, what we are going to get is at this sandwich between position, we are going to add this new group right here. Okay. So now we add 2. We cannot go no more. The reason why is we only have 2 hydrogen that can be deprotonated. So after that, we are going to hydrolyze your ester, and then if you just say I'm going to also heat it up right after, then that will give us our final product, this acetone at this alpha position, that you are going to have an acyl group, plus you are going to have this alkyl group that you introduced from the second reaction. So all in all, from the top left, our beta ketone ester through 5 steps. Number 1, we have enolate, and in number 2, we introduce a alkyl group. Number 3, we repeat to make another enolate, and number 4, we introduce another primary alkyl halide, and then number 5, we undergo the hydrolysis plus the decarboxylation. We will have a disubstituted acetone at alpha position. So that is the acetoacetic ester synthesis. Now let's talk about how to approach this kind of synthesis problem. So if I say you need to start from the acetoacetic ester, I want you to make, for example, make something. Let's make something look like this, for example. What is your thought process? So what we are going to look for is the acetal part. Okay, this is my acetal part. This is my acetal part. So this is not changing. So meaning what? Meaning this alpha carbon is where we introduce our alkyl group. So in this specific case, the alkyl group is this part right here, boxed in the red. So basically what we are going to see, what kind of alkyl bromide that we can use to introduce our alkyl group. So that is what we have here. So this is that carbon, that red carbon. So that carbon, right, this little carbon right here need to have a good leaving group to have that primary alkyl halide. So that is the red one that I draw here. So in order to go from the left to the right, we need to have step number 1. We are going to form our enolate. Step number 2, introduce our primary alkyl halide. And for this case, we only have 1 substituent at this alpha position. Then step number 3, we are going to kick off the other side, the ester side, by hydrolysis and decarboxylation. So that is how we approach the synthesis question from a acetoacetic ester to a substituted acetone at the alpha position. The next reaction we are going to talk about is from the malonic ester. So it's called malonic ester synthesis. And if we recall, what is malonic acid? That is when you have this dicarboxylic acid that is 3 carbon away. That is malonic acid. So when we have the malonic ester, so basically those carbonic acid will have another group to form this ester. So a lot of time what we are looking at here is this ester is called diethyl malonate. So that is the start of this reaction. So why we need this reaction? The whole purpose here is we need to find a way to make an alpha position substituted, alkylated carboxylic acid. We want to make something look like this. Okay. And theoretically, we have our carboxylic acid. This is our alpha position that we can make the enolate. However, when you have a base that introduced to this starting carboxylic acid, what's going to happen is instead of to form enolate, you are going to have this proton on the carboxylic acid be deprotonated. So instead of form that enolate that is less acidic proton at alpha position, you are not going to get that. You are going to get a carboxylate. And if you have a carboxylate, if you have a alkyl halide, for example, if you have this primary alkyl halide, what's going to happen is you are going to have an SN2 reaction that's going to form another ester. So that will not to achieve the alpha position alkylated carboxylic acid. So that is why we are using the malonic ester synthesis. So if we start with our malonate, so again at this position right here, this 2 alpha hydrogen is relatively acidic. So if we have our base, for example, some isoxide, this isoxide comes in, going to grab one of this hydrogen. This time I'm going to draw like this, and I'm going to form the first enolate. That OET and this enolate. And again, what you can do is you can draw out several resonance. The first one will be something like that. The carbon have that negative charge, and this can also keep resonance to this carbon right here, oxygen right here, to have another resonance. So all in all, this just showing you that this enolate that formed is relatively stable, very stable, means that hydrogen, the red hydrogen, alpha hydrogen, is very acidic. So this is my enolate. So for this enolate will attack one of the primary alkyl halides. For example, we have this ethyl bromide, so I'm going to use a green color to show the reaction error, the nucleophilic attack. So the carbon-oxygen double bond will reform, this pi bond will attack, and then kick out the leaving group SN2 reaction mechanism. So what we are going to have here is we are going to have a alpha position that have an alkyl group substituted in. And at this moment, it is still a diester. So for this diester, we are going to kick off that ester group by using the hydrolysis, and we are going to have both sides become a dicarboxylic acid. So for dicarboxylic acid, we have this 2 carboxylic acid group close by, and we are going to perform another decarboxylation. So by using the heat, we are going to redraw this molecule to make that one of this OH group hydrogen is kind of closer to the oxygen of the other carboxylic acid, and this hydrogen will be deprotonated, for example. Okay, deprotonated, and then that bond between oxygen and hydrogen goes to form this carbon-oxygen double bond, which is a CO2, and then at the same time, this bond will break. So again, what we have here is decarboxylation. What we are achieving at this moment is this eno, and at this position you are having that SO group, plus you have this OH group that original from one side of the carboxylic acid, and also you have your carbon oxygen double bond. So this is the driving force. This is how to drive to the reaction to the completion. The carbon dioxide is expelled out of the reaction as a gas. So what we are seeing here is this is our eno. So eno is not as stable as a ketone. So undergo the eno ketone tautomerization, we are going to have our carboxylic acid at this alpha position. Now you introduce a new alkyl group. So that is how we can achieve a alpha position alkylated carboxylic acid. So this is a very similar idea to the acetoacetic ester synthesis. And the difference here is, as a result of this reaction, what we achieve is at alpha position of a carboxylic acid, we can alkylate that position. So alpha position alkylated carboxylic acid. That is the result of this reaction. Now let's look at another example. Now we are going to start with our diethyl malonate, okay, to synthesize a carboxylic acid. This carboxylic acid look like this. Let's just draw something crazy. Okay, so that's one, and then on this side we have something look like this. Okay, so and 1, 2, and we are going to have carboxylic acid right here. Okay, so now we know that the whole purpose, the whole goal of this diethyl malonate can achieve a alpha position substituted carboxylic acid. So this is my carboxylic acid. So the whole point here is I'm going to look at this alpha position. What substituent is introduced? So the first one, what we see is this substituent. So in order to introduce that group, we have to have a primary alkyl halide. So this is the first one I can use. The second alkyl group I introduce here is this group right here. So come to the carbon, we have this membrane, and then we have one more carbon right here, and then we are going to use this primary alkyl halide. So that is the pieces. So how to achieve this reaction? Again, we will introduce one of the alkyl group at a time. So the first we are going to use our sodium isoxide to form the enolate, and then we are going to introduce, let me introduce a green piece first. We are going to introduce my primary alkyl halide. So at this time, what I have is the first alkyl group introduced onto this alpha position. Okay, and we'll do the second one since we have another hydrogen right here that can be deprotonated, form another enolate. So we'll have this enolate and put in another of this primary alkyl halide, and that will give us the second substituent, the alkyl group that is introduced. So this is the first one, the green one, and now I also have the second one comes in. And how to get the final? Throw in the hydronium for the hydrolysis, throw in the heat for the decarboxylation, and then that is how we achieve to have the substituted carboxylic acid at the alpha position. So that is the end of this video.